Let us discuss this theorem. So in this theorem, what we have a sequence xn, which is Cauchy. This is a given thing. And what we have to prove? We have to prove that sequence xn is convergent if and only if it has convergent subsequence. I hope all of you are familiar with the concept of subsequence, since already we have studied in first year and second year. See, subsequence, that means when we have any sequence, suppose we have a sequence x1, x2, x3, x4, some terms are there. So we collect few terms from the original sequence and we will form a new sequence, that is called subsequence of a given sequence. So that means if I consider a new sequence x2, x5, x8. So basically we have collected sequence, okay, we have collected terms from an original sequence and we are forming a new sequence. So therefore we call it as a subsequence of an original sequence. It is similar to a subset. When we have a set, in subset what we do, we take a point from the original set and we form a new set, so that is a subset. So similarly this concept we have, okay. So see, if and only if part is there, so we need to assume one part and we have to prove the second part. So here first I have written the basic information that sequence xn is Cauchy. I have assumed sequence xn is convergent and converges to x. So now our target is to prove it has convergent subsequence. So I am taking one subsequence. Let xnk be a subsequence of sequence xn. Okay, so I have taken one subsequence of original sequence xn. Now I am going to prove, yes, this subsequence also converges to the same point x. So using epsilon definition, we are going to do all these things. So let us take epsilon first. Let epsilon greater than 0 be given. Let us use the given information. We have what we have, xn converges to x, right? We have xn converges to x. So therefore, by definition, what can we write? So therefore, for above epsilon greater than 0, there exists n belongs to set of natural numbers such that d of xn x less than epsilon for all n greater than or equal to capital N. So simply I use definition of convergent sequence here. So see, for subsequence xnk, okay, for subsequence xnk, obviously nk is greater than or equal to k. Okay, for subsequence xnk we have this relation. See here, then what can we write? I will call it as 1. Then from 1, d of xnk comma x less than epsilon for all nk, okay, for all nk is greater than or equal to k. And if I consider k is greater than capital N, then we get this one. Getting? So simply using definition of convergent sequence, we proved that subsequence is also convergent and converges to the same point. Getting? So therefore what can we write? Therefore subsequence xnk converges to x. Okay, so we had taken any arbitrary subsequence, so here we proved that. Okay, so it has a convergent subsequence. Therefore sequence xn has convergent subsequence. Getting? So in this way we proved if the sequence is convergent, it has convergent subsequence. So now we have to prove converse part. Now we are going to assume it has a convergent subsequence and we are going to prove it is convergent sequence. Make a screenshot of it. After that we will go further. See, in converse part, we assume the sequence xn has convergent subsequence, say xnk, and converges to x. Now we have to prove that yes, given sequence is convergent. Okay, we will prove that that sequence converges to the same limit x. Let us prove. I will start with the epsilon. Okay, since epsilon is required. So let epsilon greater than 0 be given. Let us use the given information. We have xnk converges to x. So therefore, for above epsilon greater than 0, there exists natural number n1 belongs to set of natural number such that what can I write here by definition? D of x n k comma x less than epsilon for all nk greater than or equal to capital N. Get it? See, what will I do? Instead of epsilon, I will take epsilon by 2. Okay, so this is the adjustment. I will call it as 2. Epsilon, instead of epsilon, I am taking epsilon by 2. See, as well as we have one more information, that sequence xn is the Cauchy sequence. So let us use, we have sequence xn is Cauchy. Sequence xn is Cauchy. As you can see here, they have mentioned it is a Cauchy sequence. So again, we can use the definition of Cauchy sequence. So therefore, for above epsilon greater than 0, there exists n2 belongs to set of natural number such that d of xn comma xm less than epsilon for all n comma m greater than or equal to capital N2. So here also obviously I am going to do one adjustment, that is instead of epsilon I am taking epsilon by 2. This is inequality number 3. So 2 is true for capital N1, right? 3 is true for capital N2. Let us take maximum of N1 and N2, then both of them will be true simultaneously. So let N is equal to maximum of N1 and N2. Then 2 and 3 will work for this N. Okay. See, no more spaces there. Make a screenshot of it. Then we will go further. See, these two very important inequalities are kept as it is, and let us go further. So I am considering d of x and x. So I am going to use triangle inequality. So this is less than or equal to d of xn xnk plus d of xnkx. Okay, so d of xn xnk. So this type of thing we have. So this is less than epsilon by 2. And yeah, from 2, this is less than epsilon by 2. I should mention for all n, nk greater than or equal to capital N. So as we have defined capital N, which is true for, that means both of 2 and 3 are true for this capital N. So that's why we can write it. So it is not required. Let me remove this part now. Okay. So epsilon by 2 plus epsilon by 2, what we get? This is epsilon. So therefore, what we get finally, d of x and x. We started with d of x and x less than epsilon for all n greater than or equal to capital N. Therefore, sequence xn converges to x by definition. Getting? So therefore, what is our conclusion? Therefore, sequence xn is convergent sequence. So we started with this assumption that sequence xn has a convergent subsequence, and we proved sequence xn is convergent. That means the reverse part, converse part also we have done here. So in both ways we proved. So therefore we can declare this result, proof of this result is over. Thank you. Bye bye.